Now we will see review on the single stage amplifiers. There are three major categories. First is common source amplifier. The source is grounded. The input is going on to the gate and output is on the drain. So we find out impedance RL on the load drain side. So you can implement the load register using register itself or diode connected load or current source or other variant active loads. And also there's some source degeneration technique. We use RS. On the source node we can put some register there. For the source follower, that is common, the left is common source. Common drain is source follower. People use more often source follower rather than common drain because its action, its behavior is more like a follower, the following the input. So we have a load RL, the output and input. Here the output here. In this case, a load can be either resistor or the current source, resistive or current source. For the common gate amplifier, the input is tied to certain bias voltage that is DC, so it doesn't change, meaning it change in AC response. This is 0 volt, just AC grounded, and input voltage on the source node Vin. In output, you will see some voltage through the certain load RL. The load can be resistive load or current source load, similarly as the other amplifier. Another third one is the cascade type. So cascade is another variant of the common source amplifier. So we place the two transistors in series. So input is coming in on the top. Certain bias voltage VB applied here. That is DC, so AC ground. So this kind of structure loaded with some resistive or current source load. This structure. And also this structure can be used for the folded structure, so the intermediate node will have other so for example we have another folding node. We have current, previous case current is flowing from top to bottom. The signal is also signal current going this one branch, going through this one branch. For the folded cascade structure, we have two identical, two similarly connected amplifier stage, and we take the how do I draw there? So folded structure, we have for example cascade PMOS. Here the output load, it can be either a register or whatever, it can be register. But the input, this is a bias, finite bias here. Input coming in, so we have a current source here, like this kind of structure. So for the V in coming in, it converted onto ID current variation. This current variation is observed by the second stage amplifier. This is the common base amplifier, right? The signal current is folded, right? So the direction change, AC direction current is AC current direction changes. So here going up and down here, so this requires 2 additional branch to make it folded. So we will see more detail in the later. So this is some of the brief review on the amplifier topologies. The first one is common source stage, and second one is source follower, third one is common gate amplifier. Largely we can say that this cascode can be combination of a common source and common gate. This combination of those two that lead us to some cascode structure. Okay, cascode and the folded structure. In this example, we will see common source amplifier design. To properly bias this, let's say we input is biased, let's say at the VB, and on top of that bias we apply the small variation V in, like this. So if you apply the small, so at the input VB, around the VB you apply some signal, and the output, at the output you will see amplify the output with some common mode. So we have to determine the proper level of the current through this device. Let's say IDS. To determine the proper size of the proper level of the current level, we have to first identify what is the required range of the this amplifier at the output. First, at the output, the device can go up as much as how much? The maximum voltage can go as at the output range, the VDD. The lowest level would be where? So if you assume the AV is large, so AV is large, so the input signal fluctuation is so small, then we will assume that VB is around the DC level because the input is so small. So in that case, this M1 will get into triode region when the VDS is below the overdrive voltage of that input device. So let's say the overdrive voltage is the VGS equal to VTH plus V overdrive, right? So VGS is like this, overdrive voltage is certain voltage. So VGS is equal to VB here in this case. So the minimum voltage it can go down is the V overdrive voltage at the output. That is VGS minus VTH, meaning VB minus VTH. This can be approximated assuming AV is large. Right? So this is the output range, signal range, to make sure M1 in saturation. For the input range, you can approximate around the VB level, that is where. So above this is the gap is, let's say this is the VTH 0. So above the VTH we have a V overdrive voltage. So your signal can move around here, right? So maximum without distortion will have how much you can go up and down around by the only overdrive voltage, right? This is overdrive voltage, right? So once the swing above the overdrive voltage, then the transistor will be completely off because the gate will be, the M1 will be turned off. So as long as the M1 is stay alive, that is okay. So in that case, the maximum input range is around between this range where this is VTH versus, so input range is VTH versus 2 overdrive, around the 2 overdrive voltage. This is around 2 times overdrive voltage, right? So our purpose is to maximize the output range because the gain is large, so output swing will be very large in this scale. So we want that output common mode level to be between those two. So we want to design the output VOCM with VOCM that want to be designed that to be half of the VDD plus V overdrive of the input. Once that is determined, then we know that ID current, that is the same as IR, the current through the IRD, that is what? That would be the R over delta V. So delta V across the RD is what? The RD. So RD over VDD minus VDD plus V overdrive, half of that, right? This is common mode. Take that. That leads us 1 over RD times half the VDD minus V overdrive, right? So for proper signal range, the current through this stage is almost given. The V overdrive voltage compared to VDD is a very small number, so this can be easily approximated 1 over RD times half of VDD. So this is the appropriate current level for this device. Once that is determined, current is determined, right? That we size this M1 device. So overdrive voltage, we need to find out required overdrive voltage. What that would be 2ID over, GM. Require the GM or the 2I over the overdrive voltage. So we know that the ID is given by that one, that the equation 1. So 2 times over overdrive times what? 1 over RD times VDD over 2. So the GM becomes approximately how much? There would be VDD over V overdrive times 1 over RD. So once you determine this the topology, the GM, you can design your GM by having different size of the M1, but having different size will determine the overdrive voltage, but you don't have much freedom to change the current, because to maximize output swing, your current level, desired current level, is fixed by equation 1. So that leads us the GM that we can use for this device. So for this kind of a typical common source amplifier, then the AV will be GM minus GM times RD through this equation. As you can see, small signal current will flow through only RD. So given by the second equation, so GM is VDD minus over V overdrive times 1 over RD times, that gives us RD, that leads us VDD over V overdrive. So gain of the common source amplifier, it can be approximated by that supply voltage divided by overdrive voltage. We'll also take a look at the large signal behavior. For example, if the input is swept from 0 to VDD, then what's gonna happen on the output node? So for example, if the input is 0, the M1 is turned off. So R1 is connected to the output, so it will go to VDD up until the input goes up to VTH. Once the input Vin goes above the VTH, then the NMOS will start turn on. So at that moment, once that M1 is turned on, M1 will be what? This is off region. Then it becomes the saturation region, right? Up until, so as we bring this input voltage higher and higher, then the output node will go down until the input voltage at that point A, the input gate voltage is high and drain voltage is just below the VTH, is below the gate voltage. In that case, this is at the edge of saturation and triode, right? We are on the bringing this device on the boundary. So here, up until that point, the device is in saturation. Once the V in goes above that level, then device will be in triode region. So the available for the amplifier, the available region for the amplifier is in this, where the GM is well defined and also the sharp gain can be achieved by this. Once the device going into the triode region, we know that GM collapses. So that's why we get the slope of this curve, input transfer curve doesn't show a sharp slope. So as you can see here, so ID versus VDS, as you increase the VGS, right, the current changes. Amount of a delta ID over delta VGS is defined by the GM. But once the device is going into the triode region, as you can see in this graph, the delta ID is kind of small, so you cannot get as much gain as in the saturation. Once the device is in the triode region, we can model the network of a network in like this. This is the voltage control old resistor. Its resistance is what? In triode region, 1 over mu n COX W over L, V over drive voltage, right? In a typical common source amplifier, if the input is small enough so that the input coming in, the output will fluctuate. So for example, if the input is the biased on this VO level and the input moved around the V0 like this, then the output will be amplified, so it will go up and down. But if your output common mode is not well defined, or input signal is too large, then your signal will be clipped like this. For example, if your supply voltage is limited like a VDD and signal is too large, or your gain is too large, then your signal will be distorted. Instead of like a sine waveform as in the input, you will get like a distorted output. Such kind of a large signal behavior if you consider that such case, then input is moving around the certain bias level, and then VGS moving around, your transistor operating point will move around. In that case, so you will have a different current level. By changing current level, you will see the difference in the output. You are changing the voltage at the output. If you track the operating point and then find the transconductance, you will be like this, because if you increase the inputs, for example, like when the input is at the proper bias level, then your GM is maximized. And if the input is going down, VGS goes down for this M1, so GM goes down. Once the input goes approach to VTH of the M1, your GM will collapse like this. GM goes down, and then when the input going up, then you get the large current through the R1 and drain of the M1. So the GM goes up like this. So if you apply the large signal on the gate, your actual GM, small signal parameter like a GM transconductance, is moving around. But if you apply like a small signal, appropriate small signal onto the gate, your output is well within the operating region. Your GM variation will be limited, right? In that way, you can get more linear response. By having proper range, by having proper input and output signal range. So it is very important to identify what is the allowed input signal range on the input and the output side always. So without identifying your signal range, it will be very difficult to good circuit response, like a linear response. Once your signal is distorted, it would be difficult to recover that. So having notion of a signal range is important. In undergraduate course, we haven't talked about well enough, but in actual circuit designer, you have the such concept of the identifying the signal range. We just looked at the resistive loaded amplifier has the limited voltage gain that is approximated VDD over V overdrive of this guy M1. That because we see the bias current and the output range is tightly coupled, so there's not much room for having large gain. To increase the gain, we can change the resistor RL with the current source. The current source can be implemented with the PMOS device with some bias like this. So we apply the V in and V out. Ideally, the output, the MOS transistor will have a finite R0. Our output impedance is infinity, but in reality, R0 is finite. So RO is something that you can think of, and also for the PMOS current source will also have a finite the output resistance. So that can be what? So if you make this transistor, the ideal. So this guy and this guy, the ideal. So if we in the ideal, then we can make this non-ideal components ROP and RON outside like this, right? So AV, so the AV equal to what? So V in, so current through the input device is V in times GM, right? So AV is V out over V in. Small signal analysis we are doing, so the output will be minus the GM times ROP and RON, right? The current times the resistor, that will give us the output voltage V out. Current direction is the going upward for the resistor there. So output, the overall the voltage gain can be found like this. In this case, if you assume that the ROP, if you reuse the ideal PMOS current source, then the AV will be just minus GM ROP RON. This RON, we know that from so we can write down the equation for GM and RON. So GM is, we know that I2ID over V overdrive times the RON, output of the resistor, the output resistance from the transistor would be the proportional to L and the inversely proportional to ID, right? So we have some proportionality factor VE. So we can write down the overall gain is 2L VE. So overdrive. So if you have a larger L and smaller overdrive, then you can get some higher gain. So this voltage gain is a lot greater. This is greater than resistive loaded gain like VDD over V overdrive. So typically, if you want a higher gain, high gain, we want to place the resistor instead of resistor load. We want to have a current source load like this, right, for having larger gain. So for even higher, when you design the circuit high gain, we design the low overdrive voltage, meaning we have a large, so low current density from M1 by sizing large W, and also we want to have a larger the L for higher output resistance. But if you change this, if you have a very low overdrive, we know that we are moving toward the sub-threshold region, and also if you want to have a larger RO, you get the large L. That means larger input capacitance. So this kind of this results in a large CGS eventually, and then that reduces the FT, goes down, becomes slow. So there's some trade-off between low frequency gain versus the high frequency gain, whether you want to have a high gain, this curve, or whether you want to have a even little lower gain, but if you want a higher gain and certain frequency range, then you might want to have a different idea of a lower GM, lower L, smaller L for the higher midband gain. But if you only care about the DC gain, then you may design for the large L and small overdrive. But the small overdrive, again, this will have some penalty because we are limiting input signal range. So all these factors, like what? So linearity and gain, and DC gain, and the high frequency gain. Linearity, DC gain, and also there's all these are so mingled, and some trade-off there. Also there's a noise issue, noise thing. In terms of noise, you want to maximize the GM, but such kind of choice will sometimes reduce if you make it if you achieve the high GM by smaller overdrive, then you are limiting your linear range. So that all these things are coupled, and you have to know and understand what is the impact by your design choice. Okay. In diode connected load, we can use some special feature from it. So diode connection, you connect the gate and drain. This is MMOS case. For PMOS device, the PMOS, so we have a NFET and PFET. Again, gate and drain is connected, right? So in this case, we can find that equivalent small signal resistance. So in this analysis, we will assume that the device is in saturation. So assuming the properly biased. So now we will drive some small signal circuit, and then trying to find the equivalent impedance. So let's say, so in this example, so the other terminal is ground. Assume that the other terminal is grounded. We apply the Vx test voltage through it, right? And then measure the test current. If we know the test voltage and test current relationship, we can find the equivalent impedance. Equivalent impedance is Req is what? So Vx over Ix, right? So let's try to modulate this voltage. Then we will see the current variation on the transistor. That current, let's say, so this is small signal current. So we assume the Ix is coming in. So we will drive that. We will have a convention of a small signal currents Ix and Vx for the voltage. So having voltage variation will result in current variation. This current variation will go through the source and drain. If there is the current variation Ix there, the voltage difference will happen between gate and source, that is Ix over Gm. This node is 0 volt AC ground. We know that the Vx is equal to what? So from this equation, Ix over Gm. That leads us equivalent impedance, small signal impedance, Req equal to Vx over Ix equal to 1 over Gm. Similarly, we can find the PFET equivalent impedance, Req, that is also same as the MMOS cases. If there is current flows like this, then voltage difference will be, well, if the current direction is from down to up for the Ix, then the voltage variation will be what? Plus minus there. That is Vx, Ix over Gm. Then we get same equation, right? And this right hand side, this equivalent small signal equivalent model is for your reference. If you consider that the output resistance there, so for example, we have a diode connected. So if you consider output resistance RO, what happens is this part is ideal, we are assuming, meaning RO of this part is just infinity. So we take out the RO of a non-ideal effect. The RO of that guy is explicitly we took out outside of the transistor, we placed in parallel like this. Then this model is exactly same as what? So this model GM V GS, right? So this is the gate. So gate is tied to drain. I'm sorry, this is current model. So this is a VGS like this, right? So every time you see the transistor, it is very inconvenient to draw the small signal equivalent model. We will directly analyze using this transistor symbol. We know that how this transistor works, right? So in this case, on the left hand side, we know that that is equivalent to 1 over Gm. On the right hand side, we are gonna place in parallel 1 over RON. So overall resistance is 1 over Gm in parallel with 1 over RON. In parallel with RON, right? So this is how we get the equivalent resistance. So now let's take a look at the effect from the back bias. So typically in this configuration, we tie the body to ground. In that case, whenever you change in source node voltage, then VSB changes, meaning that results in some current variation by the VTH modulation changes, right? According to the equation IDS, half UN COX. Even though the VGS is modulated, there's another factor that VTH, if the VTH changes, that also results in the IDS variation. So we can model that in small signal analysis using the backgate transconductance GM. So basically, so in this formation, this is AC ground because this is the not VDD is not varying. This is AC, that is AC ground. So now we have a VX changes that will result in what? This is ground. So let's see if we draw that current direction. So AC current direction you can specify by the source to drain and or the drain to source in either direction is fine because that is just a variation of the current. But for the DC current, must always, large signal current should be always flows from drain to source. But right now we are doing the small signal analysis. It is okay to draw the current direction in either way. For this case, if you change Vx, then we current will change. An amount of current will be Gm times what? Vx, right? And also the additional variation by the Gm body. The body VSB changes according to Vx variation. So GMB times Vx is there. So total amount of current will be Gm plus GMB Vx. So the overall, so this is the Ix, that is I equal to Ix. So the R equivalent resistance looking onto the resistor source node will be 1 over Gm plus 1 over Gm, 1 over Gm plus Gm bar. So if you consider that the RO, output resistance, is shown in here, you can make it in parallel with the RO like this. So far we just looked at the small signal analysis, but we can also always look at the variation, the output variation we can expect is that the maximum Vx variation is that from the VDD, the maximum VD range. So Vx can go up. The maximum Vx voltage it can go is VTH below that threshold. So VDD minus VTH is the maximum voltage that ensures the M1 in saturation. But the below lower limit, there's no limit. Maybe it can go down until the ground, right? So this is the range of the Vx in typical large signal sense. But usually at bias level, if your circuit is biased at that level, and that level will be VDD minus VTH plus V overdrive voltage. So if you have a large overdrive voltage there, your output swing, if there's any swing around that, the swing can move around only this part. If your swing is bigger than that, then it will clip like this, right? So there's not much signal room for such diode connected load. We can also find the equivalent impedance looking into source when you have a GL, finite load impedance is attached to the drain side. So let's find out the Rx. This is very important and interesting because you will see why. So when you wanna find the equivalent resistance there, so any input voltage is shown here will assume that there is AC ground 0. So that is connected to the DC voltage, meaning there is no change, assuming no change. And that means the AC ground. Now we apply the test voltage and test current, or the test current. We wanna see the relationship between IT and VT. From this do we know that there, if there is the IT there, variation is in here, we have a backgate effect and the gate voltage change. Both gate, if you change the VT, then our VGS and VSB both changes. So because of that, our resultant current will be IT. So IT will be what? So this is VT, so GM times VT plus GMB plus GMB times Vx. This current will eventually go through the GL. The voltage drop across the GL would be IT times GL. That will give us the Vout. Because this VDD is tied AC ground because of the no voltage variation. So finally, the relationship between the IT versus VT, here is T. VT is just VT, IT is equal to 1 over GM plus GMB. It is quite interesting, in this equation, there is no GL involved. Because this voltage variation on the Vout doesn't affect the current variation through the transistor. So this kind of a common, this is kind of a simple structure there. We can, by putting the this device, we can isolate. There's a source node of we can isolate the source of the M1 and the drain side of M1, right? So no matter what the GL is connected, we are seeing the 1 over GM, right? In this exercise, we will consider that, let's say we connect the gate to drain, so we make a diode connection. Let's just ignore, for simplicity, ignore GMB for simplicity. Then if you wanna find the equivalent resistance here, then we apply the VT and IT there. So IT coming in through this device, this output voltage will be IT times GL, right? If there is IT there, the voltage drop across the gate and source will be what? IT minus GM. So finally, we can find the by KVL, so VT equal what? GM over IT here, and plus IT times GL, right? So our equivalent resistance is what? VT over IT there. Oh, sorry. So this part is the IT over GM. So that would be 1 over GM plus a GL. So unlike the previous example, in this case we are seeing the GL in that equation. So it is equivalent to, for the diode connection, GL, it is equivalent to 1 over GM there, right? Like this. But so as you compare with the different case in the previous example, in that case you connect that to AC ground. For the gate is tied to connected to AC ground. In that case, no matter what the GL is, R equivalent is 1 over GM, right? So this is here 1 over GM plus the GL. So this result and that one you can take a look at and see why those different is coming from. You must understand the difference. So in this case, right, GL like this, right? Now let's analyze the small signal gain. For GM, for small variation in input, it will result in GM times V in current variation. That will go through this output load impedance. That is what? Looking into load impedance from the source, that will be 1 over GM plus GMB. So considering RO is infinity, something like that. So, and once you have a GM and RO in parallel, most of the case RO is a lot bigger than 1 over GM. So even without this approximation, like the RO in parallel like this, typically RO is a lot greater than GM. Why it is possible? Why such approximation is possible? Because the GM times RO is kind of a voltage gain out of a single stage amplifier that is typically greater than 1. So around 10 to 20 or something like that. That is around 10 to 20 in modern CMOS technology. Okay, so the AC gain is output voltage V out will be found V out minus current GM times V in times load impedance 1 over GM plus GMB. That results in this equation. So GM first, M1 GM of the M1 is GM1 and GM of the M2 is GM2 and 2, like that. That's 2, 2, 2, 2, 2. Now let's identify the signal range in large signal sense. For the output range, as we mentioned, that the maximum voltage it can go for the output side is what? VDD minus VTH, right? That is maximum. But the lowest voltage would be, in order for this M1 is in the saturation, we want that to be V overdrive 1, so this guy. So at bias, we know that VGS is biased by VTH plus V overdrive 1. So M1 of the M1 overdrive, that sets the output, minimum output, the voltage range. For the input, so we know that the input is biased at the VTH plus V overdrive. It can go down up to by only lowest voltage is VTH, and the largest is kind of limited, but from the bias we know that up and down swing range must be equal, so allowed input signal range is like only this much, right? So 2 overdrive 1, right? And maximum. If we ignore the body effect, then overall gain will be GM1 over GM2. Ignore body effect. So now we know that GM equation, 3 GM equation that we are thinking of, we can have. One is, do you remember again? 2I over V overdrive, that is first, and the second one is UN COX W over L V overdrive voltage, and third one is what, square root of the 2 mu n COX W over L ID, isn't it? Right? So from this equation, if we use the, let's say, the M1 size of the M1 is W1 over L, the M2 is W2 over L2, let's say like this size, then we use the equation, which one? So for example, second, what would be the same? For the bias current, because we are sharing this branch, the current through M2 and M1 is the same. So ID ID1 and ID2 is the same. So use the third one to represent this small signal gain. So minus square root of the GM1 is 2 times mu n COX W1 over L1 times ID divided by square root of 2 times mu n COX W2 over L2 times ID. So that equation gives us what? W1 over W2 times L2 over L1. As you can see there, the gain of this diode connected load just defined by the device size ratio. Device ratio will set the gain. But if you want to have a very large gain, then you want to have a small load device, right? But again, out of this kind of a stage, the maximum achievable gain is quite limited by this kind of a size ratio. In this example, diode load is implemented the PMOS transistor. So the gain is minus GM1 times 1 over GM2. So, but in this case, the PMOS device has a different mobility ratio than compared to MMOS device. So we have a mobility ratio in this gain equation, other than in addition to the size ratio. If you use the different GM equation there, for example, so GM equal to what, mu n, this is another GM equation using the overdrive voltage here, then we get the different equation like this. So if you have the COX can cancel out, right? You can also represent the gain in terms of mu n over mu p times WL1 over W over L2 times overdrive voltage of the amplifier 1, overdrive voltage of the amplifier and the M2. So ratio of the overdrive voltage and also can affect the gain. You can look at the gain in this equation, or you can look at it that way. So changing in size will result in the overdrive voltage. So you can thing either way. To when you design the circuit, you monitor the overdrive voltage, right? VTH plus overdrive voltage, VTH plus overdrive voltage 1. So VGS and VSG and the W over L, the size, those are design parameters that you can play with. But what doesn't change in this configuration is the current through this device is shared. So because the sharing this branch, meaning the same current will flow going into the source of the PMOS device and pass through, going into drain and going out through the source. So this kind of a current path has sharing the branch, so all the devices sharing the same current. Okay. In previous examples, we are using the gain with we're having the diode connected load. The problem with the diode connected load is that if you want to increase the gain, so AV equal minus GM1 times 1 over GM2. So GM of the load transistor should be minimized. But as you can see, the GM of that guy is 2I over the overdrive voltage. If you share that current through this device, then the gain cannot be, it is difficult to achieve very large gain, because the current for the sharing the current only results in the small gain, because only the variable you can play with the overdrive voltage of the M1 and an M2. The overdrive voltage range is not that large, so to make a change onto the overdrive voltage, you have to change the device size. But the device size also, you cannot make this M2 make it small as you want, because that eventually the current is shared through the M1 and M2, so the maximum gain out of such a small device will be limited by the device ratio. To enhance the gain, voltage gain, we can reduce the current through the M2 in bias conditions. So by placing the DC current source in parallel with M2, so the current through M2 now becomes MI1 minus IS. So small current can flow through the M2. In that way, we can increase the output impedance 1 over GM2 by having smaller current. So in that way, we can have the larger gain. For example, ID2 is 1/4 of the I1. By flowing I3, IS equal to 3 over 3/4 times I1. Then the overall gain will be like this equation. So we get the 4x larger, actually 2x larger voltage gain out of this kind of configuration. This is just something that you can think of if you really want a little higher gain, so you can play with this kind of technique, the current source in parallel with the diode connected load. So this is quite popularly used technique when you require a little more gain in your circuit. Okay. So the question is, the question is how we can come up with the gain enhancement factor. You can play with the different equation. You will always get the similar result. For example, say GM1 is, let's say, 2I1 over V overdrive voltage 1, right? Times GM2 is 2I1 1/4 of the I1, right? Divided by what? V overdrive 2. We know that the under bias condition, so I1 times I have 2 V overdrive 2. If you haven't changed the device size, what would happen for the overdrive voltage? If you let's say that what would happen is that so this one will be what, -4 times V overdrive 2 over V overdrive 1, right? Now if you haven't changed the device size W2 by reducing the current through that device, that will result in the smaller overdrive voltage. How much smaller overdrive voltage? So the I2 was from I1 to 1/4 of the I1. So device current went down by 4 times, meaning overdrive voltage of the M2 will go down by half, right? O2. So that one results in the OV2, so -4 times V overdrive voltage, half of the original. So V overdrive times that one will give us a 2 overdrive voltage 1 and 2 overdrive voltage 1. So previous example, the gain was like this, but we get the another 2x boost. You can think that in this way or in that way. Either way, you will end up getting the 2x larger voltage gain when you have a 4x lower current through M2. So in this derivation, I just assume that W2 L1 L2 and W1 over L1 is the same, right? If you keep these values the same, if you place the current in parallel, you will end up getting 2x larger. In this case, the V overdrive 2, VOV2 is something that before change. So V over 2 here is after change. You get the another V overdrive 2 prime and prime, and you will get like this, right? So V overdrive 2 is in this equation is before IS attached. Okay.